Welcome to this 7th webinar from the Performance Optimization and Productivity Center of Excellence, POP. My name is Brian Wylie. I'm from Juelich Supercomputing Center in Germany, part of Forschungszentrum Juelich. And the topic of this webinar is going to be large-scale application execution performance assessment. I'll start with an overview of some large-scale applications that I have some experience with, and some of the challenges which show up when we start to try and measure and analyze the performance of these applications. I'll introduce the Scalasca toolset, which is developed here at Juelich Supercomputing Center as one tool which is designed for such challenges, and show you a case study where we looked at the performance of one of the applications on our JUQUEEN BlueGeneQ system. There'll be an opportunity for questions at the end, so please submit your questions through the corresponding panel on the GoToWebinar pane, and then I'll try and answer those at the end, or if necessary, we'll follow up by email. So let's get going. I'm sure you're aware that the current high-performance computer systems are based on distributed memory compute nodes, and those compute nodes consist of one or more processors, which may be many-core or multi-core processors. And each core of those processors will also support several hardware threads and have vector instructions. So we have a lot of different levels of parallelization and concurrency to exploit in such systems, especially since large computer systems have very many of these distributed compute nodes. There can also be accelerators, which I'm not going to discuss here, but that's an additional level of heterogeneity that can be introduced and additional complexity. I'll mention a little bit about the JUQUEEN computer system that's currently being decommissioned here and replaced by its successor, but it has 28,000 compute nodes, each with 16 cores, capable of running 4 hardware threads. That means that we can have simultaneous execution on the full machine of over 1.8 million application threads or MPI processes. An application code that's trying to exploit this machine, the full machine, will need to have high concurrency. It will need to exploit and sustain that high concurrency throughout its execution. And that's within various constraints, such as the limited amount of compute node memory per compute node. On the JUQUEEN system, there's 16 gigabytes. That's 1 gigabyte per core, or 1/4 of a gigabyte per hardware thread. So if you're trying to run 1.8 million application processes, MPI processes, that's going to be pretty constraining. Another aspect which I'm not going to deal with in this presentation is scalable parallel file I/O. This was a topic of a previous webinar, and I refer you to that for more information. In Juelich, we collected codes together that scaled and used effectively the entire JUQUEEN system into a HiQ club. We had a very flexible set of criteria for qualification. They could use strong or weak scaling as suited their application case, either looking at a fixed problem, which they tried to solve in a reduced time as they add more cores, or scaling up the problem size as additional cores were added. We insisted, or as much as possible, we looked for realistic test configurations for qualification, but we accepted that some file I/O for checkpointing, etc., could be disabled. We had 32 codes which qualified for membership of the HiQ club, covering a broad spectrum of application fields from science and engineering, and they were written primarily in standard C, C++, and Fortran, often mixed combinations of these standard languages. MPI was used almost ubiquitously, and then additionally some form of threading, mostly OpenMP. For more information about the HiQ club, there's a URL at the bottom, or you can refer to an article that was recently published at the DOI on the lower right. But this next slide here shows an overview of the scaling behavior, the strong scaling at top left and weak scaling at bottom right of the codes in the HiQ club. And the part that I think is primarily interesting is the part on the right-hand side, where we look at how they ran their application. We have a number of codes here, there are 3 codes here at the top, which were only using MPI, running 64 MPI processes on each processor. Some only used 32 or 16, so just 1 per core. Then in the middle, we actually have additional codes which are using a moderate level of hybrid parallelization. So primarily MPI, but with a small amount of OpenMP threads per MPI process. And then at the lower part here, these last codes are, again, hybrid codes, but it's usually only 1 or 2 MPI processes per processor, and with larger amounts of OpenMP threads or POSIX threads, usually 64, sometimes only 61 or a different number. So we see that both MPI can be used within constraints, but it's primarily hybrid codes combining MPI and OpenMP that can effectively scale to use these large compute systems. A code rarely scales and performs well when it's first parallelized and run on the system. Our experience is that each doubling of scale exposes a new issue that needs to be addressed. That can be a correctness issue that needs to be looked at primarily and then needs some debugging before you then look at how the application performs and perhaps think about how to tune it to perform more effectively. And each time the code is extended or an optimization is applied, this process needs to be repeated and verify that you haven't introduced any correctness issues, that the optimization is improving the performance that was expected. At Juelich Supercomputing Center, we have simulation laboratories and cross-sectional teams which work with application developers to improve their codes, and that brings an effective team together. We also have had regular workshops, 1 a year typically, where we had an opportunity for a select number of codes to get an opportunity to run and try their application on the full JUQUEEN system and look at any scaling issues that came up from that. The applications, as I've mentioned, are a mix of languages, a mix of programming paradigms. The tools need to support this, and the tools need to be able to give information at different levels. Firstly, an overview of execution performance to get a high-level picture of what issues might be there, and then for more in-depth investigation to figure out what's the origin of those issues. The tools have access to different forms of instrumentation, can measure different aspects, but it's typically not the case that you want everything all of the time, because the more information that's collected, the more instrumentation it's added, the more impact that's likely to have. Every measurement that's done inherently has an impact on the application execution itself. Additional code is being executed, additional information is being stored in memory and is going through the caches. And in the worst case, we would actually have to write things to file during execution, but we would try, if possible, to store things in memory and only write files at the very end where it has no impact on the measurement itself. Impact's generally negative, as you can imagine, but there can be cases where execution time does increase. That's part of the complex nature of the interaction between the instrumentation and the measurement that we're doing. So there's a careful balancing act required to use the limited resources, what information is collected, what measurement is done at different points in time, and what processing is applied to it. We're primarily interested in parallel application performance, as well as what's coming at the local level for each processor and core, where you're looking at the computational intensity, the cache utilization. We're primarily looking at how the processes and threads interact, where there are synchronization issues, where there's data transfer issues. And if there's a measurement impact that modifies the execution of a particular process or thread, it will typically propagate when they interact with other processes and threads, and in the worst case, there will be a cascade of interactions, ultimately affecting all of the processes, which makes the whole measurement very difficult to interpret. There are different forms of measurement which are possible. One form is a profile summarization, which is done during execution, where we can collect information on each process and thread about what it's executing. The amount of information in this case will grow with the number of processes and threads. An alternative is that we may want a complete event trace of what each process and thread is doing as it's executing, and this amount of information will increase in size with the number of iterations, the number of time steps, and typically with the duration of the measurement itself, because we would want to store all of that information buffered in memory during measurement and then only write it to disk at the very end. So the more that's collected, the more has to be written, the more has to be processed. When we're dealing with large-scale applications, then we're just going further with this. We have many processes, we have many files to deal with. This can become a file system bottleneck, and the more that we can collate things and combine things together as effectively as possible, the more efficient the whole measurement will be. As the amount of data grows, we'll also have much more data that will overwhelm our typical analysis and visualization processes. If those are serial processes trying to load all of that data into memory and process it, then we need a very large memory node, some special purpose node for that. So typically we would try and parallelize the analysis as much as possible to minimize this bottleneck. So my recommendation would be to always profile extensively prior to attempting trace collection. There's much more information in the trace, but the profile already summarizes that, and we can score that profile. We can get a good estimate of what the trace collection requirements will be, not only the total size on disk, but also how much memory we would need to buffer on each process to avoid needing to flush traces to disk during measurement. Any trace which won't fit in memory is probably too large to deal with, whether it's too large for measurement or too large for analysis. So there's a refinement process that needs to be employed here. The defaults of collecting as much as possible might be reasonable at small scale, but as you scale up, that will typically be too much. So be selective about what is collected, or filter out things which are not so valuable. There may be many frequently executed routines which are very short and quick that can produce a disproportionately large measurement overhead, and those are good candidates to avoid, to filter out. If you would like more information and collect some additional hardware counters, additional metrics, those can be added as well, or you can also define regions of interest to use some specific loops or blocks of code which you'd like to have additional structure in your analysis. That applies both for profiling and tracing, but if we're dealing with a trace measurement, then the duration is an issue. The first few iterations or time steps of execution typically have some warm-up costs that may not be representative of the full execution. So just recording one or two is usually not enough, but you don't need to typically record thousands or millions of time steps. It may be 100 or maybe only 10 is an adequate number. And we'll have a corresponding reduction in the trace size. The Scalasca toolset was designed and developed specifically to support scalable performance analysis of large-scale parallel applications. It's based on this community-developed SCORP instrumentation and measurement infrastructure, as well as the Cube analysis report utilities and Explorer GUI. It's combining flexible runtime summarization and event tracing to address both of those measurement and analysis options. The initial focus was on MPI and OpenMP applications, but it's been extended to support additional threading paradigms, as well as accelerators and information from accelerators. And it supports the common HPC systems, the BlueGene systems, the Cray systems, K-computer, etc., as well as large clusters based on Xeon processors or Xeon Phi, as well as power and other architectures as well. I'm not going to have time to go through all of the details of using Scalasca, but just to quickly give an idea of how it works, we use SCORP for instrumenting the application, to have our instrumented libraries linked with the application, so that when the application executes, each process and thread is collecting information, and that information can then in one form be summarized into a profile on each process and then written to a summary report for presentation. These analysis reports are what I was referring to, can be analyzed and can give an indication of what could be improved to refine the measurement, to optimize what's collected, to add additional information into the measurement. They also give us a good estimate of the amount of data that would be required for that would come from tracing, and how much memory we would need to allocate for the trace collection. If we then set a different environment variable, we can run a trace collection measurement that will again use collection of events into memory on each of the threads. And then at the end of the execution, we would write a trace for each process and thread into a separate file, and those can be then analyzed. They can be analyzed by Vampire for trace visualization, or they can be analyzed by the Scalasca trace analyzer, which does a weight state search in parallel. It is replaying the application execution, determining what events get transferred between processes and threads, and using that information to derive an augmented weight state analysis report, which has additional weight state information incorporated into the metrics that are included. So I'll quickly show you an example of how this looks. I have a cube file that was collected on our BlueGene system here. It was run in a very small configuration here, just with 32 MPI processes. Each of those MPI processes has 16 OpenMP threads. And by expanding the tree on the right-hand side here, I'm able to see the execution time in this case on each of the application threads just over 7 seconds. I can get a breakdown of which application functions were executed here. I'm looking at the functions which were executed and collected in the measurement here. We see that the one which had the majority of the time was this AXI routine. So that's one of the main hotspots of the application execution. And then we can also see in a call graph presentation, call tree presentation, where that was executed in the application code. So it's highlighted down here. It's inside the parallel region of the CG conjugate gradient iteration, which is the main benchmark, the main core of this application execution. If we were to look at other metrics here, we can expand the time hierarchy. We can distinguish what was execution time, which we were looking at, from what is reported as idle time. There's very little idle time within the CG kernel itself, but there's a lot of idle time during some of the setup process where only the master thread is active, and you see activity on the master threads here, but all of the OpenMP threads were idle. There's no OpenMP used during that setup process. It's just using the MPI level of parallelization there. That's part of the initialization, which we're not so interested in, so we can focus our attention on the CG solver inside the parallel region. We can expand break out the execution time into the part that was computation. Most of the time is computation, which was nice. We see there's a very small amount of MPI time and a little bit larger amount of time in OpenMP overheads here. So we're in a parallel region. If we see where the OpenMP overheads are, we see they're a little bit further down, particularly down here. And if we expand the metric hierarchy, we see it's mostly synchronization time. Synchronization in two forms. We have some critical time and a critical section up here. So that's the critical section where we have actually lock contention being the main cause of waiting there. And we also have a number of OpenMP barriers. And those OpenMP barriers are also where there's waiting time that we can see various examples of. These are some of the main ones that I've highlighted here. So we can see at a glance where the main inefficiencies are, the main additional costs are. We see how they're distributed across the MPI processes and threads, but even with this very small measurement, we see with 32 processes, we have a lot of information. We can't really get a good overview of it all using this tree presentation, so we provide a statistical presentation here where we can actually get a better perspective on the variation of time across the processes. So the minimum here is 0.04, the largest is 0.63, the mean in this case is 0.55. So we see at a glance that the variation of time or whatever metric is selected across the processes here. I'll go to the MPI, because the MPI is the main cause of the waiting time in the barrier, because each of those barriers is preceded by a master section, which is only executed by the master thread. I can hopefully see that here. So we see that all of the MPI behavior we see here and here, these are all MPI operations which are done within a master section, so they're only executed by the master thread. This is a funneled mode of hybrid parallel execution. And that means that whenever we have a process that is doing some MPI, the other processes are waiting at the barrier that immediately follows that. So we could expand the MPI hierarchy and see some waiting times that are happening for the collective and the point-to-point operations. There's some waiting time that's the majority of the time in the all reduce, or we have waiting time for point-to-point operations at the all-to-all here. These are the sorts of things that would be effective or costly for a parallel application execution at large scale. If, for example, I look at the time in the waiting time in the all reduce, we can see at a glance that the different processes here are showing up with higher amounts of time than others. Wrong. So there are 8 processes here, which actually are the 8 ranks which correspond to the corners of a 3D decomposition. It's a 4x4x2 decomposition of 32 processes. Those are the 8 ones in the corner, and they have, in this case, more time in the all reduced, so they're spending more time waiting. We can see the amount of data that is transferred in the all reduced. They're all transferring the same amount, or we can look at the number of MPI communications. We can look at the number of communications, the number of receives that are being received in the wait hall, and we see a very similar pattern here where some ranks have a very different number of communication partners from the others, and therefore have a different communication cost associated with them. So I think there's many more metrics that we could look at, but that gives you an overview of the sorts of metrics that are collected, the information that's available from the trace analysis, and how it's presented by a tool like Scalasca using this cube presentation here. This application that I was looking at here is Nekbone, and that's going to be my case study that I'll continue with. So Nekbone is a proxy application for the NEC 5000 CFD solver. That's a large complex application. Was part of the Coral benchmarking, so there's a specific data set that was provided. It's a weak scaling data set where there's a fixed number of spectral elements defined per process. And we were running it on the JUQUEEN system here with a single MPI process and 64 OpenMP threads per process on our BlueJean system, the BlueJean Q. What we see from that execution and what we were expecting is that it scaled very well from the smallest scale of execution here, which was a single rack or half a rack, all the way up to the full machine. That's the behavior we were expecting from this benchmark. But maybe it's not telling us the whole story, because you'll have heard of various efficiency metrics in some of the previous webinars. If we take a look at those, we see that some of the efficiencies look very good throughout the scale of execution. There's a little bit of diminishing of the computation efficiency at the very largest scale, but basically there's not very much change in computation or load balance. They're all pretty good here. What's affecting the efficiency, or the main efficiency detractor, is serialization efficiency. Here it's about 0.7. That has the biggest impact. It's combining the impact of serialization, synchronization of OpenMP threads, and synchronization of MPI ranks as well. So that's the sort of information that we can get from the POP efficiency metrics, but we would like to see where that's occurring in the program and what's the cause of it. And as we saw before from the Scalasca trace analysis, there's very little inefficiency, there's very little time in the MPI behavior. That scales very well. That's primarily because there's only a limited amount of interaction with neighbors. There's only 26 neighbors in most cases. Whereas the OpenMP part, we see at the bottom here, the lock contention is an expensive thing. We see the waiting time at the explicit barriers, which were introduced after the master sections. Those are where most of the inefficiency is occurring, most of the serialization is occurring. So the application scaled well to the full size of the BlueJean system, but when we looked at the efficiency, serialization was something was highlighted as something where it was impacting on performance. That's because there's a synchronization between OpenMP threads within each process. There's a fixed number of threads as we scale up. That's not changing, so the synchronization is not changing. The amount of synchronization is not changing. And likewise, as we scale up to the very large configurations, there's only a limited amount of MPI synchronization and interaction with neighboring processes. There's only at most 26 neighbors, so that's also not changing. And that explains why the serialization inefficiency doesn't change as we scale up. It's an impact, but it's a fixed impact as we scale all the way to the largest scale of the system here. Part of it, inefficiency, is by the nature of the funneled execution, where the processes which are doing additional MPI work are the ones which are causing serialization time to build up on the others. And there's also an additional load imbalance from the fact that the corners have less work, less communication to do than the edges of the face, but those are negligible as we use a 3D grid with a very large scale. you can neglect those. They don't change again with scale. We also saw that there was a small computational degradation for the very largest execution. My theory at this point is this was because it was a non-power of 2, only for that, only at the very largest scale where we had 28 in the Z processor dimension. Potentially that non-power of 2 was causing the computation to be less efficient than using 8, 16, 32, which it was using for the smaller configurations up to the full size. We instrumented the application with the IBM compilers here. We were also getting additional information from OpenMP, which we instrumented with our own tools and interposing on the MPI library, all of that done by ScoreP. That allowed us to collect profile measurements, which we could score and used for determining which routines were not contributing value to our measurement, and then filter those out. There were half a dozen routines filtered out in these measurements. When we were doing summary measurements, we could also include hardware counters. That was quite costly, causing a significant dilation to measurement, but if we don't have the hardware counters, the measurements are much more efficient and less costly on the BlueJean system. I also show some statistics for the largest measurement, the trace measurements, which we did, which produced a trace size of just about 1 terabyte. For that, we needed a measurement buffer of just over 200 megabytes on each MPI process to be able to store and collect and collate all of the measurements at the end of the execution and write the data to disk. So these are quite substantial costs, and these costs, the trace size, the memory size, those were increasing with the scale. So if we're running at half the scale or a quarter of the scale, those numbers go down proportionately. Likewise, the size of the analysis reports that are produced as a result of running the trace analyzer or the runtime summarization. So we were able to do we have a number of codes that are highly scalable that can effectively use many thousands of compute nodes, many cores. And we have tools which allow us to profile and collect event traces for those. Scalaska was the example that I showed you in a quick demo here, but there are other tools which could be used as well. The amount of data that's collected in the profiles or in the event traces is typically growing with the number of processes and threads, and that requires appropriate schemes for managing that data and some judicious reduction mechanisms to avoid collecting more data than is valuable or can be handled effectively. I only had time in this webinar to discuss one example of a measurement which we did on the BlueJean system with up to 1.8 million threads. We've had other measurements which we've done on Cray systems with up to 250,000 or 240,000 MPI processes, or using the KNL system, where we again had a hybrid application with a total of 256,000 OpenMP threads. Those are just a few selective examples which came up in the course of the POP analysis work. There are many others that we have seen in the course of using the JUQUEEN system and other systems as well. So this is getting close to the end of my session here. I didn't have the time to go into a lot of detail about the POP efficiency metrics, which were covered in a previous webinar, but there's also a lot of information at the learning section of the POP website about those. You can get more information about the Scalaska tools, and the sources for downloading and installation are available as open source, as well as user guides and quick reference, additional information about the metrics. I also wanted to mention that there are tutorial exercises and case studies which are produced by the Virtual Institute for High Productivity Supercomputing, which we work with, and they have a trace training event which is coming up in a week or so's time. It'll be in London. It's a free event, and I think there's still some places available for that. So if you're interested in coming along and learning about Scalaska and ScoreP, as well as the Barcelona tools and others, that's a good event to get more information and get some experience with using the tools. So that's the end of the material I have for presentation. It's a good opportunity if you want to ask some questions to send those in. If you have suggestions for additional topics for webinars, you can send them to the email address on screen here, or if you have additional comments or feedback from me, you can use the email address at the beginning of the presentation. But I think that I see that we have one question. Can I explain what FOM is? FOM was the figure of merit that the benchmark defined as what they were looking for scalability. The figure of merit was, in that application, it was the floating point performance, so the number of floating point instructions that were executed per second that were increasing as the application scaled up. So that was just how the performance was defined for that application. So there's a second question here. Can I explain how to interpret the critical path report? I didn't explain it. I can quickly show it, which I think is easier than trying to explain it. If I can do that quickly. There's a critical path here. When we were looking at the total execution time, we saw there was about 7 seconds of execution for this application on each of the application threads. So if I look at the total execution time, each thread is executing about 7 seconds. So the critical path through all of the application code is about 7 seconds, and we can get a breakdown of which routines show up on the critical path. There's a couple of seconds in this initialization setup, which I said we were not interested in. There's a couple of seconds here in this AXI routine, and correspondingly smaller amounts for the other parts. So the critical path gives us an insight into what is the bottlenecks and how the bottlenecks change with time. The code that's on the critical path is affecting the performance. What's not on the critical path won't affect the performance because it's not the bottleneck that is preventing things from going faster. So what's on the critical path here is computation. And by expanding the critical path, we can also determine how much of that is because of imbalance. So things where activities are on other processes and threads that could have been distributed or executed in a different order, and that would have been able to reduce the critical path from over 7 seconds to, in this case, down to about 3.5. How does Scalasca relate to the OpenMP tool API, which has just been published as part of the OpenMP standard? Scalasca and ScoreP is working on using that tool API. We don't have support for it released at the moment, but it's certainly something that we're experimenting with and developing. At the moment, we're using our own instrumentation of the parallel routines. So here we see a parallel section which was instrumented. All of these barriers, critical sections, are things that our source code instrumenter processed from the application sources to put in the additional instrumentation necessary to collect that information for our analysis. In the future, we're hoping to get similar information from the OpenMP tools interface. At the moment, we don't get enough information or all of the information we would like, but that's where we're trying to, what we're developing at the moment. One more question. Is load balance efficiency in Scalasca and other tool use the same definition? Almost certainly not, because I'm not sure how it's defined in other tools. I think that each tool is free to define load balance efficiency in whichever way they find most appropriate. I would have to check the definitions of the other tools, and you'd have to check the definitions or compare the definitions yourself. Here, the definition which POP uses for load balance efficiency is how the computational time, the compute time on the slowest processor thread compares with the mean. So that's gives you a measure of how far the slowest one varies from the mean. Other tools might have different definitions that they can use at different points in time. But it's certainly a measure of how much you could hope to gain if you could redistribute the computation so that you didn't do any more work, but you shared it equally across the processes and threads, so they all did exactly the same amount without having any more additional overhead. Okay, I think that there are no more questions I see in the queue, so I'll close the webinar at this point. Thank you for attention. As I said, we welcome your suggestions, ideas for future webinars, and there's much more information available at the POP website.